In this video, we're going to do some practice problems with set operations. So we'll do 3 questions. For the first one, if A is the interval containing 0 up to 2, and B is the interval starting at 1 containing up to but not including 6, we want to determine the following, where our universe is the entire real number line. So these are not discrete sets, these are continuous sets, so I'll show you how to work with these. Okay, so it's a good idea usually to draw these things. So we have A looks like this, 0 to 2, and then B, we'll do B in red, and let's say 1 all the way up to but not including 6. So we have a line that looks like this. And first we want to take a look at A intersection B. So here's the question, which is in both of these? Well, we see this overlap here from 1 to 2, and it includes both of those. So our intersection is going to be the set, or the interval from 1 to 2 inclusive. So we can see that if x is in A and x is in B, then x is going to be in A intersection B. So we have that overlap there. For A union B, we want to take a look at the whole thing here. So we have from 0 all the way up to 6, but not including it. So A union B is the entire span of both sets. B minus A is a little bit different. So remember, our B is in red here, so I'll put B in red. Our A is in orange, and we want B minus A. So we want all of B except for where A is. So A covers 0 up to 2, and including 2. So if we subtract all that, our new set, I should not use orange for this, let me switch to light green. This should include a little bit past 2 all the way up to 6. So we get this open interval from 2 to 6. And finally, our last one here, A complement. Well, A complement is everything in the universe minus A. So A is only from 0 to 2 inclusive, which means that the complement of A is going to come from negative infinity all the way up to 0, but not including it, because 0 is in A, so 0 can't be in A complement. But then it also includes everything just after 2 to positive infinity. So we have to use a union to describe this set, because essentially we have everything to the left of A, and we have everything to the right of A. So that is what our A complement would look like there. Okay, so that's the first question. If you can do this with these continuous intervals, then you should be able to do them with discrete sets, no problem. Some questions might be a little bit trickier, however, where instead of given sets A and B and finding the union or complement or the intersection, you may be given some operations and have to find the original sets. So in this question, we have to find set A and B, but we know that A minus B is 1, 3, 7, 11, B minus A is 2, 6, and 8, and the intersection is 4 and 9. So what I suggest doing is actually making a Venn diagram for these things, especially if the amount of items we're counting are very small. So A is going to be a little bit bigger than B. So first of all, we know our intersection is going to contain 4 and 9, so we can put 4 and 9 in there. B minus A is going to be 2, 6, and 8. So we know 2, 6, and 8 are going to lie in this area over here. And for A minus B, we have 1, 3, 7, 11. So we know that 1, 3, 7, and 11 are going to be in this space here. So we can see our sets here. So we can see that set A is going to be 1, 3, 4, 7, 9, and 11. Because remember, we include everything in its set. And the set B is going to contain 2, 4, 6, 8, and 9. So the question is, how do you do this without Venn diagrams? Well, you know that B intersection A is 4 and 9, so 4 and 9 have to be in both sets. And we have these B minus A, so that means that B minus A, 2, 6, and 8, those have to be in just B. So we put those in B, and then we end up with this 2, 4, 6, 8, 9. Then we take a look at A minus B, and we see 1, 3, 7, and 11. So these 4 numbers must be in A. So we put those in A, and we end up with this result. If you weren't given the intersection, things might get a little bit trickier because you don't know which numbers could be in both, but for this question we're given it, so it's not too much of a problem. Okay, the second question. Third question. We're going to do some more proofs just like the last example video. So here's the thing. If A is a subset of B and C is a subset of D, then we can prove that A intersection C is a subset of B intersection D. We can also prove that A union C is a subset of B union D. So what do we do here? First, we're assuming these things, so we can use this information. A is a subset of B and C is a subset of D. And our first assumption is going to be that some element is in A intersection C. So we're going to say, let X be in A intersection C. So what does this mean in English terms? This means that X is in A and X is in C, and this is just by definition. So here's the thing. We know that A is a subset of B and C is a subset of D. So if X is going to be in A, then we know that X has to be in B. And if X is in C, then X has to be in D. Okay, so now if we use the definition, we know X is in B and X is in D, so that must mean that X is in B intersection D. And there you go, there's our proof. So we have shown that if X is in A intersection C, then it must be in B intersection D. For the next part, it's the exact same process. So first we assume that X is in A union C, and by definition, this means that X is in A or X is in C. Using the definition of our subsets and our assumptions, we know that because A is a subset of B, X must be in B, or if X is in C, then that means that X is also in D. So we have this X is in B or X is in D, and then by definition that means that X is in B union D. Therefore, we have proven that if X is in A union C, then X is in B union D. Okay, so that was the 3 questions in this video. If you have any questions about these questions, or if you suggest questions for another video, please leave them in the comments below. I will check them and respond to them as quickly as I can.